So this is the last part of the nitrogen cycle we're going to cover in this chapter, and this really has to do with nitrogen isotopes. When we talked about carbon isotopes, hydrogen and oxygen isotopes, they're really important tracers for us to understand some of the inner workings of the cycling of elements. Nitrogen isotopes have developed recently to serve that same capacity. And you'll see within the book that there's a box that's unique to the second edition that I had written for the authors that really talks about the role of nitrogen isotopes and how we can use them ecologically to better understand ecosystem processes. Just as with carbon, for example, having a heavy isotope and a light isotope, same thing with nitrogen. We have N15 and N14. N15 is the heavier isotope of nitrogen, and it just has one additional neutron. Chemically, they're more or less exactly the same, but they have different physical properties that generate differences in reactivity and other factors associated with those compounds that have N14 in them versus N15. There's only a certain set of reactions that discriminate more strongly against N15 than N14. So if you have, for example, ammonium, and that ammonium is N14 instead of N15, there are certain processes that are going to discriminate more strongly against the N15 containing ammonium than the N14. Knowing which processes these are really important, because when we look at the products of those processes, we can see sometimes a lot more N15 in there than N14, and we can infer the relative importance of those processes. So nitrification is a really important discriminating step. And as nitrification happens, it discriminates more strongly against N15 than N14. So as nitrification occurs, for example, that the ammonium becomes enriched in N15, and the nitrate is going to be more likely to have N14 in it. So therefore, if you look at plants, for example, in a system where there's some nitrification that happens, if the plant is relatively enriched in N15, you can infer that it was primarily acquiring ammonium. If it's relatively depleted, it's more likely to have acquired nitrate, all other things equal. For this to be true, there has to be just partial nitrification, so some nitrification that's happened. It can't go to completion, for example. And since we know that nitrification discriminates against N15 containing ammonium, that this pool is going to become enriched in N15, the ammonium pool, and the nitrate is going to be relatively depleted in N15. So nitrification is the first process that discriminates strongly against N15. Gaseous nitrogen loss is another situation that discriminates strongly. So for example, if you have ammonia, for example, that's produced from ammonium, that this is a process that discriminates strongly against N15 containing ammonium. If you look across ecosystems and want to infer the relative importance of ammonia production, those that have a relatively enriched pool, all other things equal, of ammonium and N15 might be ones that have greater ammonia production. In addition, denitrification also strongly discriminates against N15. So when you have a lot of denitrification that happens, the remaining nitrate pool, all other things equal, becomes enriched in N15, and the products are relatively depleted, and they tend to have a lot higher concentrations of N14. The last process that discriminates strongly against N15 are mycorrhizal fungi transfers of nitrogen to plants. So remember, some mycorrhizae take up nitrogen and transfer these to plants. When that happens, there's a process at the interchange that leaves N15 behind and gives plants more of the N14 containing compounds. So anytime you have a lot of mycorrhizae that are transferring nitrogen to plants, those plants should be more depleted in N15 and the mycorrhizae enriched. To summarize it, here's figure 9.13, 9.13. And this again is a real basic representation of the nitrogen cycle. You have soil organic matter that generates dissolved organic nitrogen, ammonification that generates ammonium, and then nitrate during nitrification. These arrows right here that are relatively large and have gradations on them represent fractionation. So when there's ammonia production, N2O production during nitrification, or gaseous nitrogen loss, or nitrification, these are all discriminating steps. So ammonia production is going to enrich the ammonium pool, nitrification enriches the ammonium pool, gaseous losses during nitrification or denitrification also enrich the remaining pool. Nitrate leaching does not enrich the pool for the most part. And then transfers of plants through mycorrhizal fungi tend to enrich plants. In contrast, direct uptake of dissolved organic nitrogen, ammonium, or nitrate does not deplete the plants in N15 and enrich the remaining pools in the soil. The reason all this becomes important is that as you look across a gradient of nitrogen availability, plants become enriched in N15 because a lot of these processes are going in the same direction. So ecosystems that have high N availability are likely to have a lot of nitrification and a lot of denitrification, for example. That enriches the remaining inorganic pools, and plants that are taking these pools up become enriched themselves. When nitrogen availability is relatively high, plants rely a lot less on mycorrhizal fungi for their nitrogen, and so there's a lot less of this fractionating step in a high nitrogen environment as a low nitrogen environment. So low nitrogen environment, mycorrhizal fungi are really important, and they're going to be giving depleted nitrogen to plants. Put all of this together, high nitrogen availability, a lot of loss pathways that enrich pools, and not a lot of loss or fractionation that occurs from mycorrhizal fungi. Low nitrogen availability, not a lot of these loss processes that enrich the pools, and a greater reliance on mycorrhizal fungi, which lead to a relative depletion. Okay, so when we put this all together, remember, high nitrogen availability should be associated with high plant N15 because you're going to have a lot of losses and not a lot of mycorrhizal transfers. That leads to a net enrichment. If we look on a global scale, this is a synthesis that we did that was somewhere on the order of 10,000 leaves from all over the world. And they were arrayed across a gradient of temperature and precipitation. As we looked across this gradient, we saw that essentially for cold ecosystems, foliar N15 was pretty constant. Then, as the temperatures got warmer, nitrogen N15 went up. The N15 here is a relative enrichment of N15 compared to N14. The atmospheric standard that we use tends to be N2, which has a specific N14 to N15 ratio. So, greater the temperature, the greater the N15, the relative enrichment of N15 in plants, and that means that hotter systems tend to have greater nitrogen availability than colder systems. At least that's that interpretation. Across the precipitation gradient, as we go from dry to wet, when you're in wet ecosystems, you have a lower N15 than in dry ecosystems. That means dry ecosystems tend to have higher nitrogen availability than wetter ecosystems. Lastly, and this is probably the strongest pattern, we measure the nitrogen concentrations of those leaves, milligrams of nitrogen per gram of leaf tissue. And this is the nitrogen concentration of leaves. Those leaves that had high nitrogen concentrations tended to be enriched in N15. Those that had low nitrogen concentrations tend to be depleted in N15. What this means is that the nitrogen concentrations of a plant are a pretty good indication, all other things equal, of availability. High nitrogen availability systems had high N concentrations and also high N15, and vice versa. Situations where you have low nitrogen availability generates plants with low nitrogen concentrations, and N15 is relatively depleted. That being said, for a given nitrogen concentration, you're going to have a lot of variation, and a lot of variation at a given precipitation or temperature. But the general patterns hold. Hot, dry ecosystems with plants that have high nitrogen concentrations tend to be enriched in N15, and that means that the reliance on mycorrhizal fungi in these types of systems is probably pretty low, and you can expect to have a lot of gaseous loss that happens. One last way that we've used nitrogen isotopes is to better understand what's happening as far as nitrogen transfers are concerned. Here we're going to take a look at the foliar del N15, so the relative enrichment of N15 compared to N14 relative to a standard for plants that use different types of mycorrhizal fungi. Ericoid and ectomycorrhizal fungi are thought to be important for transferring nitrogen to plants, compared to our arbuscular mycorrhizal fungi and those plants that are non-mycorrhizal. They don't use mycorrhizae at all. If you take a look, there's variation, but the non-mycorrhizal plants are a lot more enriched or a lot less depleted in N15 than ericoid plants that use ericoid mycorrhizal fungi. Part of this might be the systems that they're in, but it fits because we think of plants that use ericoid mycorrhizal fungi as getting a large proportion of their nitrogen from the mycorrhizal fungi. And because it's a fractionating process, the mycorrhizal fungi tend to be relatively enriched in N15 and the plants relatively depleted. If you take a look at the fruiting bodies of ericoid or ectomycorrhizae, they're often, if you look at the fungi or the mushrooms that are produced, they're often up here. And the mushrooms are relatively enriched, so they're at plus 6, 7, 8 per mil, and the plants themselves are an equivalent amount depleted. So they keep the heavy nitrogen, give the plants light nitrogen, and it's a pretty good indication of their dependence, of the plant's dependence on mycorrhizal fungi.